This is summary of lecture 26 of complex matrices and FFT. This is a summary of chapter 9.3 in the book about the Fourier matrix and FFT. Before that, there's an important concept called the roots of unity, which is, I think, it's not explained that thoroughly in the book or even in the lecture. So let me bring some explanation here that is not mentioned in the lecture. So we're talking about a really special equation of z times z to the n equal 1. So this is a very special equation. And the way to solve that, the roots of this are this w equal e to the I 2 pi n. Okay, so let's first talk about, if you remember the quadratic equation like x squared equal 1. So this must have two roots, right? So x1 equals something and x2 equals something. And that's also the same thing that we want to find here. So in case if I have z to the n equal 1, then I must have nth solution. I don't mean like n solution to this equation. And that solution, the roots are defined by this equation. Actually the first root is this. I should say the first root, okay? So the first root. But the second root is pretty simple. It's just the w squared. And so on, you have double u to the 3 until to the w to the n, okay? So this is kind of unique and kind of new for me because not completely exactly the same as what you have faced previously when you have a quadratic equation. And right now also z represent complex plane, so we are working in terms of a complex plane that have a unit vector. So let me give you an example of how this works to give you a better idea. Okay, so let's start with z to the 2 equal 1. Okay, and even without this formula, okay, so I want to solve first without using this w, right? I will have this, and then I can break down this to this equation, and then I have the z1 equal minus 1 and z is 1. Okay, and if I draw this in the complex plane, then what do I have? And remember from previous previous node, I should say, so z, this is also equal to a plus ib, and here we have z is 1 plus 0i, right? And z is also equal to the r e to the theta I, and this will equal to like 1, which is the r, the modulus, e to the 0. So we don't have anything that contributes to the imaginary part here. So how do we put this into the complex plane graph? So of course we found out that the radius, like the modulus of our unit circle. So first let's draw the unit circle. That's not a really perfect circle, so these are a unit 1, you see. Okay, so these are unit 1. So how I draw this is simply I just have it here. Let me give it orange. So here and here, right? So this will be my z2, for example, let's say here, and this is z1, for example. So this is just 1, this is just minus 1, okay? Or I can say this is z1, z2, it doesn't matter. So I just want to point out that I can get the root, I can get how I put it in this unit circle in the complex plane by just using this formula, right? By just factoring this equation into this, and then I found the z, and then I put it here because I also know that this equal to this polar form. But now let's take a look at this equation and let's use this one, okay? So our first root, okay, this is our first root. The first root here, so that will be equal to the w is e to the I 2 pi over n, and right now our n is 2. Okay, so we put it here, 2 pi 2. So we have I 2 and pi. Okay, and this is just saying that I have a unit circle because you see this r is 1 right now, right? So I just don't put it there, but remember there's this r which is equal to 1, and then I go around the pi. So I go around the pi and I end up here. So this is my root. So this telling me the same thing as what I got here, but here I just name it z1, where this is my first root. Okay, but they're telling the same thing. So this also, if you expand it into the, if you remember, this is also equal to the r cos pi times sine pi, but now our r is 1, so we have the cos of pi plus I sine pi, then this will be minus 1, and that's exactly what we have here, like we just going to the pi direction. And how about our second root? So this is pretty simple because all we need to do is that just that we need to power through 2. So we have e to the I 2 pi. So this time we go completely to the circle, completely go around the circle, and we end up here again, which is our starting point. So this is our second root. Now what I want to say here is that, you see, I use two different equation without using the w. I just derive this from the equation, and now I'm using the w to find the roots, and they bring me to the same number, -1 and 1, which are the solution to z squared equal 1. So this is called the roots of unity, you know, the roots of the unit circle of this equation. Now I will give us another example. Right now let's do z to the 4 1. Okay, so let's first do this kind of thing here. So we know this is z4 minus 1 equals 0. Then we'll have z2 square minus 1 square like this, 0. Then we'll have z square minus 1, z square plus 1 equals 0. Then let me put it here. You have z plus 1, z minus 1, z square plus 1 equals 0. So you'll have z, the first root, the second root is 1, and here you cannot expand it further, so you'll have z squared equal minus 1. So you have z is minus imaginary. Now we have imaginary, and then we also have let me put it here. So we have the minus imaginary and plus imaginary. Okay, so these are the 4 of this are our roots. Okay, and if we follow what we have did here, then we can simply draw them also in the unit circle. So where are our roots? We have 1, we have minus 1, but now we have those that contributes to the imaginary part, which is the I and minus I, right? So 1 minus 1, I minus I. So these are all our roots. Okay, and now let's also give a shot for using this equation. So we will first find our first root, which is e to the I 2 pi now over 4. So we will have e to the I half of pi. So we are only going like halfway through the pi. so 90 degree of the circle. So where do we end up? We end up here, which is pointing to the eye, right? So this will be equal to the eye. If you don't believe this will equal to the eye, let's also expand this into this form. So I have cos of half of pi plus I sine of half of pi, and this will be 0, and I have this is 1, so I have I, right? And this equal to this one equal to this one. So this is my root. I can find my root again by just simply manipulating this equation, or I can just find it here, which I will be using in my next video in this chapter. So this chapter mainly talks about using this to find the roots of this equation. And then I can similarly find, when I find that w is I, then I can easily find the next root, which is the square of w. So I square is minus 1, which is, I can see it here, right? And then this brings me again to my third root, y cubed, okay? And this will be minus I, right? And that's exactly what I have here. And then again, the last thing is to the 4. Of course, this is 1. So that brings me here. So I just want to put this to here because it's a really nice example, I think, and then it really grabs my understanding of these roots of unity, and they are unevenly spaced point, right? They are unevenly spaced point. As you can see here, if I have n of 2, it's evenly spaced around the circle. If I have 4, it also evenly spaced around this circle, and the same thing goes if I have 4, 5, 6, or any number that you want. So that's about the root of unity. And I will talk about the Fourier matrix, which use this property of finding the roots in the next video. Thank you.